So let's just chit chat. Anybody wants to run a restaurant or a cafe? No? Y'all want to be engineers? Nobody? What about Subin? What about you? Why not? I mean, do you guys like going to a cafe? How many of you go to cafe and work? Yeah. Okay. So Junho, right? Yeah. What would be your, if it's up to you, if it's up to you, how would you schedule serving your customers? First come, first serve? It's not very efficient. But your goal is to maximize profit. And let's say like all your classmates arrive at the same time, right? There's limited seats and you could take the order first. Who would you seat first? So whoever buys more, but they might actually take longer to leave. Yeah, I would take whoever stands a lot the most, but who's actually taking it outside, right? Yeah. So manufacturers, obviously, but you also have to think about customer service, right? The reviews that they will write, right? Reputation, right? So if you think about a lot of system issues, they're pretty analogous to the things that we run into at life as well, right? So sometimes you want to simplify things, make it simple to implement, or sometimes you want to go very fine grain, which could be complex. But either way, not everybody can be happy, right? So you have to set your principles and just follow it. So let's talk about proportional share scheduler. So some people call this fair share scheduler. So what it does is it guarantees that each job obtain a certain percentage of CPU time. So it's not really optimized for turnaround or response times. Okay, so if your goal is fair sharing, other metrics you might have to sacrifice. So the basic concept here is we use something called tickets, and tickets represent the share of resource that a process should receive. Now the percent of tickets represent this share of the system resource in question. So a simple example, we have two processes. Process A has 75 tickets, process B has 25 tickets. So we basically have 100 tickets. And since A has 75% of it, it would receive the 75% of the CPU share. So one way to implement this is called lottery scheduling. So what it does is a schedule simply randomly picks a winning ticket. And it will load the state of that winning process and run it. So here, again, same example. You have 100 tickets. Process A has from 0 to 74, it has 75 of it. Process B is from 75 to 99. Now the scheduler would run a random number generator between 0 and 99. When 63 is a winning number, then it runs process A. In the next run, it got number 85, which falls into process B, so you run B. So in the end, right, it'll be about 75 versus 25, right? And obviously, the longer these two jobs compete, the more likely they are to achieve the desired percentages, right? So again, pretty simple to implement, and you could still kind of give them the fair share. Now, fair doesn't mean 50-50, right? A has 75 tickets, so they implement a concept called ticket to basically satisfy fairness. Now, in terms of tickets, there are different mechanisms. One is called currency, right? It's like our money, the currency changes. So a user allocates tickets among their own jobs in whatever currency they would like, and then system would convert that currency into the correct global value. So example here now, we have 200 tickets, and that's the global currency. Now, process A has 100, process B also has 100. Now user A. No, I think there should be user A, user B. Yeah, my bad. Can you make a note so that I can change this? Yeah. So now user A has 100. No, I'm confused. So it's 100, it's 500. Okay, never mind. Sorry, I'm sorry. Yeah, sorry. Process A has 100 tickets. I'm sorry. Process B has 100 tickets. Now, user A uses 500 for A1, 500 to AB, A2. Now, it has 100 tickets. Okay? So it's 500 to 500. So you shouldn't worry too much about the actual value, but relative value, right? So these are same value, 500 to 500. So among 100, that should be 50-50, right? Now B, on the other hand, it has 100 tickets. It used value 10, but that's the only value. That's the only process you're running. So it should be 100. So that's the currency, right? You guys know what currency, it doesn't matter what the value is that what the number is, actually the value that matters, right? The worth, right? So here, worth of 500 versus worth 10 is different because of currency. You guys are good? That kind of confused you a little bit. We're good? All right. Now there's another one called ticket transfer. So as a process, you could actually give some of your tickets to other process. Like, why would anybody do that? Right? You might wonder, but a very famous example is a client. You're a client and your server needs to serve you, right? So when your server is serving you, you give your ticket to the server, say, please get this done quickly, right? So that's a ticket transfer. There's also ticket inflation, where a process can temporarily raise or lower the number of ticket it owns. So if any one process needs more CPU time, it can boost its tickets. So many mechanisms when it comes to fair scheduling. So in terms of implementation, so we have 3 processes, A, B, and C. And we could keep the process in a list. So here we have job A, B, and C with each ticket numbers, right? So job A has 100 tickets, B has 50 tickets, and C has 250 tickets. Again, they're on a list. Let's say you pick a random number, which is the winning number, example 300 among 400, then job A will probably go from 0 to 99, 100 to 149. So 300 is in job C, right? So you will run the C, but obviously if you want to be efficient, you probably want to sort the list from the highest number of tickets, right? So had we done that, right, we only had to traverse 2 nodes instead of 3 nodes that we just did, right? Because if you had 250 here and the winning number of 300, then it would have been on the second job versus the third job, right? It's the tiny details that impacts the efficiency. Yeah, and this is the code. I won't go through it, but this basically shows you the implementation on the previous slide. One more example. I'm so thirsty today. So we're going to use another metric called the unfairness metric. So this is the time the first job completes divided by the time that second job completes. Very interesting metric. So let's say there are two jobs and each job has runtime of 10. Then the first job would finish at time 10. Second job will finish at time 20. So your unfairness metric will be 0.5. So obviously, if it's close to 1, it's more fair. Yeah, I don't know if fair is the right word, but it's better, right? It means they are finished around the same time, so it's relatively fair. One way to represent fairness. Now for the lottery scheduling, let's say if you have two jobs, each job has the same number of tickets, and in the simulation it was 100, and you can see when the job length is not long, is unfair. So the job length, as it gets longer, it gets more fair, but initially it's not. So this is actually like still the lottery scheduling is still part of the fair sharing discipline, but you still see it's not completely fair. Obviously, it depends on the metric, but you can't really satisfy everybody. So if you think about everything we learned so far on the proportional share, it has been non-deterministic, right? There's randomness in it. So how about we actually have a deterministic approach? And that's where the stride scheduling comes in. So stride is defined as a large number, for example, 10,000, divided by the number of tickets of the process. So if process A has 100 tickets, when a large number is 10,000, then your stride will be 100. If B has 50 tickets, 10,000 divided by 50 should be 200. Now with that stride number, what we do is when a process runs, it increments a counter by its stride number. Okay. And you pick the process to run that has the lowest pass value. So obviously, if you have larger number of tickets, your stride number will be smaller, and you will be picked more often. Okay, so that's more deterministic. So an example, you have 3 different paths. A has stride 100, B has stride 200, C has stride 40. So you would probably guess that C will be run more often. Initially, they all start with 0, right? So you have to pick between A, B, and C, and let's say arbitrarily A gets picked. So A gets ran, and then its counter would get incremented by its stride. So now in the next turn, it will get 100. So now it's 100 versus 0, 0. So it's B or C. Again, you pick arbitrarily, and then B gets picked. So next time, C is the only one with 0, so C would get picked, and then 40, right? Compared to 100 versus, so C gets picked, and then finally 100 is less than 120, so you pick A, and so forth. So based on the ticket counts you have, now we have a more deterministic approach, right? Now, one drawback you could say is that now stride scheduling needs to maintain the per process pass value here, like this. And obviously, if you have hundreds and thousands, that's also overhead. You have to maintain these numbers. You have to increment, keep track. And then also, if a new job enters, right? So it will be pass value 0. Let's say everybody's now in like thousands, right? Then only the new job would get served. So that's unfair, right? So the lottery scheduling we learned before, It doesn't have per process state. So in that way, it has its advantages as well. So let's look into what the Linux operating system actually uses. It's called Linux Completely Fair Scheduler. Now, if you ever become successful and name an algorithm, I advise you not to use something like completely fair. Because that's a very subjective term. Don't ever call your work excellent, pioneering, whatever. Like people, there will be many people who judge your work and they will judge whether your work was completely fair or not. This is a very dangerous naming tactic. Anyway, this is the current CPU scheduler in Linux. So the whole philosophy of this scheduler is that I don't want to spend much time making scheduling decisions. So you're supposed to decide on the scheduling, but the point is, but I don't want to do that. Okay. But what it does is that it doesn't have a fixed time slice. It basically assigns a process time slice, a proportion of the processor. It has some priority, and it will use the nice thing we learned previous time. And it uses an efficient data structure called red-black tree. Now, we're not going to go into the data structure itself, but it does enable efficient search, insertion, and deletion of a process. So for the CFS, it uses something called virtual runtime. V runtime denotes how long the process has been executing. And this is a per process variable. So this increases in proportion with the real time when it runs. And CFS picks a process with the lowest rerun time to run next. So in principle, this is not very different from stride scheduling. Now, to go into a little detail, we have to introduce a term called SCED latency, probably scheduling latency. Typically uses 48 millisecond. Shabin, can you turn back on the AC, please? Yeah. So a process's time slice would be this value, scheduled latency, divided by the number of processes running on the CPU. So, example here, you have 4 processes, and they're basically time sharing running, and then C, D complete, and then A and B would get a larger number of slice, right? So you have a constant value divided by number of processes. So if process completes, now you get a larger slice, right? So it's not a fixed time slice. You still want to have a minimum time slice because you don't want to spend too much time scheduling overhead when there are too many processes running. In terms of priority, weights, or nice. So a nice value. CFS enables controls over process priority, and the nice parameter is an integer value set from -20 to +19. So there's a range between 40. Positive value means low priority. So if your nice is 19, it means like I'm not important. -20 means this is super urgent. Okay. Now here I also remember it's not the absolute value. It's really a weight. So here is an example, priority to weight, right? It has 40 values. So these are -20 all the way to 15. So these are all relative, basically. So we have a new time slice formula. Time slice is basically your own weight divided by all the weights combined, multiplied by scheduled latency. So a simple example, let's say we have 2 processes. A has -5 versus B has nice of 0. So what the weight would be is if you go back here, -5, 3121, 0, 1, 0, 2, 4, So you get that in. And if you put that in this formula, A would get time slice of 36 milliseconds versus 12 milliseconds used by process B. So we covered two key things. One, not a fixed time slice, but also you enable priority, right? So you do a time slice to serve, fairly, but then, hey, not, equal share is not fair. So whoever is more important would get a larger slice. Right. Yes, v-runtime with so v-runtime formula, you calculate the actual runtime, right? So with that weight, now you have to look into the actual time you have run, right? So calculate the actual runtime, scale it inversely by the weight of the process, right? So you have an actual runtime, and then you add that into your weight, the runtime, and da 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 da. Yes, and I mentioned about the red-black tree. The thing you should probably remember is that, so by having a smart data structure, instead of O of n, this becomes O log n. Yeah, so you should just know that Linux uses some interesting data structure for efficiency. We're not going to go into the actual data structure today. Yes, I/O and sleeping processes. These must be dealt with. So you don't want to have a situation where some processes monopolize the CPU when a process has a significantly small rerun time after sleeping, right? So let's say all other process has been running. Another process was in a sleep mode, then it wakes up, and its rerun time would be much smaller, right? Because rerun time is what's the actual runtime of this process in its lifetime, right? So if it was sleep, it doesn't mean you should just be monopolizing the whole thing, right? So you don't want that. So you want to set the rerun time of the process to the minimum value found in the tree when it wakes up. So in the data structure, it would have some value. It won't be like 0, right? So it's kind of like moderating it, right? Okay, you should have priority, but it doesn't mean you should basically use all by yourself. However, with this, if a process sleeps for a short period of time frequently, do not ever get their fair share of the CPU. So again, there will never be a perfect algorithm. Somebody might not be unhappy, but such is life. All right, 2/3 done today. Any questions? Yes. Right. So it's basically one of the mechanisms. So just think about, let's say you have $100 today versus if you had $100 20 years ago, the value would be very different, right? So how do you represent that in the system? So that's what it's about, really. Yeah. Yes, sir. Hold on. Let me just go to him first. Yeah.
Let's say have but it feels like if we try to when exactly the CPU is being expressed, it's overhead, right? We need to check if the CPU
Yeah.
how does it run the base? How does the OS know that the process is packaged?
So I was understanding first half, then I kind of lost. So how does the operating system know the process actually utilizing the CPU?
Yeah, like the process might be utilizing CPU or waiting to do something else. But if we try to check if the process is actually running CPU, that check is an overhead, right?
Right. Yes. Yeah.
How does it happen in the real world to avoid this overhead?
I'm sorry. So I mean, like, so you don't want to check often? Is that the question, or like? How is the overhead avoided? So overhead of whether the process is actually running.
check.
Well, when the process is done, right, then there's an alarm basically. It's implemented where your process is done. I mean, your control goes to the operating system anyways.
So the process itself.
I mean, when the process is done, right? So as a, if you're running application, right? When you're done, then you have a code, right? It sends back to the operating system. Anyway, you're done, you're halted, right? So you give that control back to the operating system anyways. That's why you have a timer. So the operating system gets control periodically to decide whether to switch to a different context.
I know those processes are happening, but they might not be spied in the secure context. So how does the process know which processes are CPU friendly and IO?
I mean, you have to keep track, right? You have some statistics, right? So even like, let's say if you run Windows, you do the task manager, if you go in the Linux space, you do something like top, right? I don't actually use Mac, so I'm sure there are tools to show what's basically, is it running process? Is it a lot of networking, communications? There are different aspects of it, right? So there are tools to actually monitor it, right? And based on workload characterization, which is a field on its own, you can decide which one is more efficient, which one is better, which one should be scheduled later, etc. Or maybe you can talk later class if there's more questions. Somebody else had a question? Is there somebody else? Yeah. Legion. Which one was it? 18? This one? Okay. So basically, this was for time slice, right? Now, this was assuming, hey, there is no history. But if you look, actually see what CFS is, it actually considers how much time you ran, right? The VRun time, right? So you're using current VRun time, what's my VRun time value? And then you have a weighted component as well. No, this is for yeah, so this was like, okay, weight of 0. So it looks like it was the initial weight. So it's actually tracking how my weight value has changed. Does that make sense? So I have a current weight and I have the weight 0. Does that make sense? So I minus 1, that's like just previous. So that would be very little difference. Can you come again? So yes. So basically, initially when you prioritize, so you have a value, but based on whether you have been processed so far, then your weight might actually change. Yeah. Does that make sense? Or if it's not clear, can I actually go to CampusWire to actually explain a little bit more? Yeah, yeah. Anything else before we go on to the address space?